Okay, it should be recording.
Okay, and hello everyone, and welcome to the first JPEG workshop on subjective image quality assessment. This workshop is organized by the ad hoc group on image quality assessment at JPEG Standardization Committee. The agenda for today is as follows. You can see it, you should be able to see it on your screen. We already spent 5 minutes and we have 5 more for me to open this workshop. So we will start with a presentation about JPEG Aic3 use cases and requirements and why we have restarted this activity by Jon Sneyers, and then Michela will review the subjective image quality assessment methods that are the state of the art for today. Then Dietmar Salpe will present us his research about subjective image quality assessment with Triplet Comparisons. And afterwards, Richard John will also present his research about unreasonable effectiveness of deep features as perceptual metric. And the last talk will be by Matthias Wien about the remote export viewing at the MPEG visual quality assessment team. In the end, we will have 20 minutes of Q&A panel. So please keep your questions until the end. We will discuss everything in the end, so to be on time with all the presentations. Here are the pictures of our speakers that I found on the internet. I will introduce each speaker separately before the talk. I just want to show you this timeline of the JPEG AIC activities. We, as I said, we recently restarted this this work at JPEG in order to produce a new standard that addresses new issues that we face today. We already have a draft call for contributions, and we are planning to issue the call for contributions during the next JPEG meeting. So if any of you will become interested, you are welcome to join the standardization process. Okay, the first speaker will be Jon Sneyers. So Dr. Jon Sneyers is a senior image researcher at Cloudinary, which is a market-leading company providing cloud-based media management, processing, and delivery services for websites and apps. He received his PhD degree in computer science from KU Leuven, and Dr. Sneyers' research interests are image processing and compression. He is also the chair of the JPEG XL ad hoc group, and he contributed a lot to that project. Also, he is the project leader for the corresponding ISO IEC 18181 standards. And in addition, I want to say that Jon is also very active in the open source community, and as far as I know, makes a lot of contributions. Jon, please, you can start. I will stop sharing.
Okay, thank you. So, hi everybody. Let me share my screen. So I'll try to introduce basically why we restarted the AIC activities, and what are the specific use cases and requirements for this new activity that we are starting. So just to sketch the context a bit, there's a lot of new image codecs, WebP, AVIF, HEIC, JPXL, and also now we are looking at AI-based codecs. And of course, they can reduce the bandwidth and storage needs, and can also allow higher image fidelity. But how to evaluate these codecs is still a bit of a problem. Objective metrics like PSNR, SSIM, VMAF, and so on, they are not reliable indicators of the actual image quality. And especially if you want to have something that works across different types of images, the metrics cannot really be used reliably to know what the actual subjective quality is. And also, especially AI-based codecs, but also in general, encoders tend to optimize for these metrics, which causes the metrics to be even less reliable, because basically the encoders are fooling the metrics. So subjective evaluation is still the only reliable way to assess image quality, but we need some new methodologies, and I will explain why. So yeah, just to make the point about objective metrics, I did some internet surfing, and I found this graph somewhere where basically people are saying, well, a PSNR of 35 is good enough. And then they show a plot like this that says, yeah, if it's 35, then if you look at the mean opinion score, that's in a good bucket. But this is actually fiction. This is not a line. And in some recent results, this is what it actually looks like. So on the horizontal axis, you have the subjective scores. On the vertical axis, you have the PSNR, and it's not a line. There is some correlation, of course, but it's very weak, and the actual image quality will depend a lot on the codec or the encoder, more specifically, and on the contents of the image. So PSNR 35 good enough? Well, sometimes it will be good enough, but not always, and it's very hard to tell. So there is another issue in quality assessment, and that's the difference between image fidelity and image appeal. So fidelity is the question of how faithfully, how true is it to the original, how accurate is the compressed image, whereas appeal is more a question of, is the image pleasant to look at? Are there no annoying artifacts? Does it look okay, basically, even without looking at the original? So in the past, like with the old JPEG codec, low fidelity and low appeal were basically the same thing. If you would go to the very low quality settings, the image would start to look very obviously artifacted. So it was basically the same thing. But with the newer codecs, especially AI-based codecs, but also the more advanced classical codecs, they are able to produce images that have a high appeal, that look okay. There's no obvious artifacts, but the fidelity is still quite low. And one problem with the traditional assessment methodologies is that they are conflating the question of appeal and fidelity. So they're basically conflating appeal with quality. Like if you look at the ITUT BT 500 grading scale, it's talking about how annoying things are. And annoying is basically a word that implies something about appeal. So it doesn't really say anything about fidelity. An image can be not annoying, but still it can be a low fidelity image that doesn't really truthfully represent the original. So in a lot of past work, the kind of bit rates that were investigated, the kind of distortions were low bit rate, high distortion. So for instance, if you look at the TID 2013 data set, which is a very well-known study of subjective quality, the kind of distorted images that are in there are really very strongly distorted images. So really, a lot of them are very low quality. But these are not really the kind of qualities that you would want to use in practice. So these are really very low quality. So the question of what quality range should assessment focus on is an important one. And this is where we basically have a problem. So in the methodology of AIC1, the first technical report that AIC made, which refers to the BT500 methodologies, these assessment methodologies work very well for the lower qualities, but they start to saturate at some point, where basically there can no longer be made a distinction between images. They are so-called visually transparent, but not really actually, because they're still quite different from the reference image. Then at the other end of the spectrum, there is the AIC2 methodology, which was developed also in the context of JPEG XS, and this is aimed at very, very high quality. So this is the kind of quality that we can call visually lossless. So in AIC2, what is done is a flicker test where the distorted image is flickering relatively rapidly with the original image, the reference image. And the question is, can you see anything flicker or not? Or basically the question is, which of the two is flickering? And then they look at the proportions of people figuring out which one it is. But to reach that kind of quality, that's really requires high bit rates. It's basically meant for a production workflow in video production, for instance, where you want to work with really almost lossless quality, but this is not the kind of quality you can afford to have on the web. So this would be like in libjpeg terms, the quality 99 or quality 100. It's very high quality. So the problem with the flicker test is, as soon as you have one pixel that is visibly wrong, it will fail the flicker test. So this only works if you're really aiming at complete visual transparency. So there is a gap in the quality range where the AIC1 methodologies don't really work anymore because they're already saturated, but the quality is also still too low to apply AIC2 flicker tests. So this is the range we want to focus on for AIC3. So just to show how it might look when AIC1 methodologies saturate. So you basically get these plots where as you increase the bit rate or set the encoder to higher quality settings, there's basically a plateauing happening in the subjective scores you get, even though these images, if you would test them with AIC2, even the 2 bits per pixel ones at the very best ones, they would still not pass a flicker test. But there's no way to really distinguish the different levels of distortion here. So the scope of AIC3 is to address this this range of qualities that we define to be the range between high quality in the sense that it's at the high end for the BT500 type of assessment, up till the near visually lossless, so the point where Aic2 starts to become applicable. So this is basically the range that covers a lot of important use cases. So both the types of qualities that you currently want to use on the internet are typically in this range. Also, the kind of quality you want for a consumer and camera are typically in this range, at the higher end of this range. So many important use cases are, we believe, in this scope. There is another aspect of the AIC3 project, which is extending the procedures to crowdsourced evaluations. So in the past, basically the lab-controlled experiments were the norm. This has changed a bit with COVID situation that made it impossible to do lab-controlled experiments, although it was already changing before, but this was accelerating the trend. Of course, lab-controlled testing has some advantages. It's easier to reproduce experiments in different labs. You're basically testing only one variable at a time, which is always scientifically a good idea. And if the testing is going to be relevant for professionals who will also use a controlled working environment, where they have some control over the monitor calibration, the ambient light, and so on, then this type of testing is probably most relevant. But crowdsourced evaluation also has its advantages. It's basically by necessity testing the actual real world situation. So there's a diversity of viewing environments, a diversity of subjects. Also geographically, they can be more spread out. But of course, the disadvantage is that there's no control over the viewing environment. Everybody will use their own screens with an uncontrolled ambient light, and we don't know most of the variables in this scenario. So in AIC3, we want to focus on what is needed to do a crowdsourced experiment, because we believe this is going to be the more common type of experiment. So we're basically looking for contributions to specify these new methodologies suitable for the quality range I just discussed. So we need something that is more sensitive to spot differences than the traditional side-by-side comparison, where like in the BT500 methodology, where you have the original image on one side, the distorted image on the other side, and then you're asked to give a score to the distorted image. But the problem with side-by-side is that it can be quite tricky to see the differences, because your eyes have to travel from one side to the other. In fact, there's a whole genre of puzzles that is based on this principle, that it's not so easy to see differences between two pictures if they are put side by side. So if they are changed in place, like with the flicker test of AIC2, then it's much easier to see differences, because basically the change will become motion of the picture instead of your eyes having to do the work. Yeah, this could be part of a new methodology where it's probably no longer purely side by side. We're looking for all kinds of contributions. It can take many forms, and it doesn't have to be a complete solution. So any aspect of the problem where relevant contributions can be made is more than welcome. The deadline will be the 14th of October. And the idea is that we will start with the collaborative process immediately. So there's no, often when we have new projects, there is a competitive process where we have a call for proposals, where everybody makes a proposal, and then the proposals are somehow evaluated and tested, and then this is used as a basis to find a starting point for new standards. Here we're going to start immediately with the collaborative process because it's we couldn't come up with a way to do the meta task of evaluation procedures. So the timeline was already discussed previously a bit, but we have the draft call for contributions already out there. It's on the website. It was published at the previous JPEG meeting. We're currently having this workshop. At the next JPEG meeting next month, we will have the final call for contributions out, and the submission of contributions will have to happen before the meeting after that, which will be end of October. This is when we will start the collaborative process, and hopefully we will have a first working draft by the meeting after that one, and a committee draft 2 meetings later. At least that's the hope. So a few more things. It's very useful if we can have some interoperability of the results, especially considering that these experimental results can have multiple applications, including training, for instance, of AI-based metrics and so on, which requires a large amount of data. So if we have some machine-readable representation of the results that we can standardize as part of this project, so that everybody uses the same format, then this could allow more easily aggregating results from multiple experiments, because of course it's always going to be relatively expensive to do subjective experiments because it inherently involves humans. So if we can combine more results, it's always going to be useful. So just to take a peek into the future. So once we have this new subjective methodology, the idea is to also take another look at objective metrics and try to see if we can come up with better perceptual metrics. These can be classical metrics or AI-based metrics, and we will have a call for proposals for new objective metrics. But in order to do that, we first need to have the subjective methodology in place so that we can have the actual ground truth to compare against, because otherwise we have no way to evaluate proposals for new objective metrics. So just some sneak preview at some of the recent results. So there are metrics better than PSNR already out there. PSNR is not a great metric. I used it as an example to show that the correlation is quite weak. There are existing metrics that have a better correlation, but it's of course still not that nice thin line that you would want it to be. But just to show that there is room for improvement there, and this is something that we also intend to do. yeah, besides the subjective metrics and the objective metrics, there's also other aspects of image coding that we can look at in these new AIC standards, like assessing things like codec complexity, encode, decode, speed, memory, and other aspects like generation loss, trade-offs between speed and density, and so on. So this can also be interesting, although it's not the main focus, of course. So in summary, the aim of the activity is to have a new subjective image quality assessment methodology covering the range from high quality to near visually lossless quality. And we are now calling for contributions. The idea is that in October we will start a collaborative process, and if everything goes well, then we should have a committee draft for a new standard in about 1 year. So if all goes well, a published standard in about 2 years. And then later, we'll also look at objective quality metrics. So the idea is to have a call for proposals for that in about 1 year. So around the time that we have the committee draft for the subjective methodology. And then after this call for proposals, there will be a competitive process. Here we will be able to evaluate proposals, and this can then maybe lead to also a new standard or technical report. So that's what I had, I think, yes. So questions at the end, I guess. So I'll just stop here. I hope I'm more or less within the time.
Thank you, Jan. So our next speaker is Michela Testolina. She will have a presentation that is called Review of Subjective Image Quality Assessment Methods. Michela is a PhD candidate at the Multimedia Signal Processing Group at École Polytechnique Fédérale de Lausanne. She is a PhD student of Professor Tourosh Ibrahimi. She obtained her bachelor and master degrees in telecommunication engineering from the University of Trento, Italy. And since 2029, she is also a co-chair of the Aic2 group on image quality assessment, the very group that is organizing this workshop. And her main research interests are in the field of objective and subjective image quality assessment and learning-based image compression. Please, Michela, you can start.
Let me share my presentation. Okay. I guess you can all see, right?
Yes.
Okay, thank you very much. So good morning or good evening, good night to everyone. As Evgeny already said, my name is Michela Testolina. I'm a PhD student at APFL, and now I'm going to present a review of the state of the art on image quality assessment. Let me just remove this bar. Okay, so just a quick outline of my presentation. I will first briefly review the previous AIC standards, then I will give an overview of subjective methods, and in particular, I will try to divide them in according to the evaluation scale and according to the presentation method. And after, I will give a brief discussion for both these two classification that I will do, and then I will draw some conclusions. So about previous AIC standards, I think it was already mentioned by Jan, that there are two parts that have been standardized. The first part reviews the methods that were already proposed in BT 500 and BT 1082. So in this case, these standards address more the qualities that goes from low to high. Then there is the second part of the standard. So we have here AIC part 2, which present new evaluation procedures for nearly lossless coding. So here in our quality scale, we are much higher. So we are in the range that goes from near visually lossless quality to visually lossless. So we have this gap that goes from high quality to near visually lossless quality that we are trying to fill with the part 3 of the standard. So about subjective quality methods. So they are just methods that aim at measuring the quality of an image as perceived by a human observer. And there are 3 main categories. So there are single stimulus method, there are double stimulus method, and triple stimulus methods. So as the name say, the single stimulus method allows to measure the quality as perceived by human observer by showing to the subjects 1 stimulus at a time. The double stimulus is that compared 2 stimuli at a time, and the triple stimulus presents 3 stimuli at a time to the subject. So in this presentation, I will mainly focus on double stimulus methods, but I will also briefly talk about single stimulus. So the first classification that I'm doing is about the evaluation scale that can be different, and I'm presenting 3 examples. So the DSIS and the Dscqs and the ratio scaling. So starting from the DSIS, which stands for double stimulus impairment scale. It's a method that was first described in the recommendation from ITUR BT500 and that are reviewed in the first part of the Aic standard. So this consists in showing to the subjects 2 images, one being the original and one being the distorted, and asking to the subject to rate the impairment between these 2 images. And the grading scale in this case is discrete with 5 levels that goes from imperceptible, perceptible but not annoying, slightly annoying, annoying, and very annoying. So a similar but different is the Dscqs, so the double stimulus continuous quality scale, which was described also in the recommendation from ITUR BT500 and also reviewed in the part 1 of the Aic standard. In this case, we are showing 2 stimuli to the subject, but we are not revealing which one is the original and which one is the distorted. And we ask to the subject to rate both stimuli. And in this case, the grading scale is continuous and goes from excellent to good, fair, poor, and bad. So in this case, they have to grade twice, one for the stimulus A and one for the stimulus B. So one example of application of the Dscqs was in the JPEG AI. So we use this protocol a lot. For example, this is a screenshot that was taken during the call for evidence, where we decided to evaluate the different submissions using, as I said, the Dscqs method. So you can see here that we show 2 stimuli, one known as sample A and the other was sample B. So we asked to rate both qualities, just moving this red part in the slide bar. Another method that is also mentioned in the part 1 of the Aic standard, and it's less known, and it's firstly described in the report from ITUR BT1082, is the ratio scaling. So this is suitable when no reference is available. And I have here in the next slide the description can be done to the can be given to the subjects, because in particular we are showing some images in a random order, and we are asking to the subject to rate the quality of all these images that we are showing. So we can give to the subject the following information. You will be presented with a series of pictures in a random order. Your task is to judge the picture quality of each by assessing number to them. Rate the first picture, any number that seems appropriate to you, and then assign numbers to successive presentations in proportions in such way that they reflect your subjective impression. There is no limit to the range of numbers you may use. You may use whole number, decimals, or fractions. Try to make each number to match the quality as you perceive it. For example, if one picture looks 3 times better than another, assign a number 3 times greater. If it looks only 1/5 as good, assign a number 1/5 as great. So let me go to the previous picture. So in this case, at first the stimulus A is presented, so all the subjects will give a score, and then after we'll assign a number in proportion. And this has the advantage that doesn't only allow us to understand that, for example, the stimulus C is has higher quality than the stimulus B, but lower than the stimulus A, but we are also allowed to understand that the quality of C is a little better than the quality of C, but 5 times worse than the quality of A. So just to have a final discussion on all the methods that I presented, we have the discrete scale that was presented with the Dscqs. I presented then a continuous scale that, for example, using the Dscqs, and a ratio scaling method that is the last one I presented. So the discrete has the advantage of being fast and intuitive. You just need to click on the score that you want to give, but does not cover a wide range of qualities. The Dscqs instead is more precise, but is also slower because you have to grade 2 pictures at a time, and also you have to move the quality in the bar, the bar for the continuous scale, so it makes it slower. And the ratio scaling is more accurately represent the subjective opinion, but does not use information of the original, and it might be slow. So I presented the different scale. Now I will discuss how you can present the different stimuli to the subject. And in particular, we'll review sequential methods, a simultaneous method, and then oscillation methods. So the sequential method just consists in showing to the subjects images in sequence. So for example, you have your stimulus A that will be shown to the subjects for about 10 seconds. Mid-gray image that will be showed for about 3 seconds, and the stimulus B that will be presented for other 10 seconds, following then the voting interface. So in the end, it will look something like this. I'm not sure if you are able to see any difference between the images, because I know that Zoom applies some compression, but here you have the first image. Here is the original, followed by the mid-gray, and this is the compressed one. And then the voting interface. Of course, I am accelerating this. I'm not leaving it for 10 seconds because of time reasons. Another method is the simultaneous. So it just consists in showing the images side by side. So in this case, also, I don't know if you're able to see it because of the compression of Zoom, but on the left, we have the original image, and on the right, we have the compressed image. And on the bottom, we might add the voting interface that could be, for example, the discrete scale that we saw before, or a continuous scale. So these 2 methods have been compared to see which one is the best in some cases. So in particular, I'm presenting the results that you can find here in this paper. So in this paper, they presented 2 subjective results conducted in 2 different laboratories, but with the same conditions. So for example, the first experiment was conducted in EBU and used a sequential method. And the second one was conducted in a PFL and used a simultaneous method, but all the viewing conditions like the ambient light, the monitors was the same, and the number of and the stimuli were the same. So the only thing that changes are the way in which the pictures are showed to the subject. So in this paper, they are also doing 2 different experiments for 2 different distances from the monitor, the first one being 1.5 meters, the second 2.7, and in red you can see the overall, so it's the one that I will be referring. So I think the most visible difference here, it's about the confidence interval, that when we have the sequential, it's much higher compared to the simultaneous. So this paper in particular was presented the results for high dynamic range videos. So they wanted to compare 4 dynamic range levels. So it's a little different than the compression use case that we are usually considering in AIC, but still I think that some conclusions can be taken. So as I said, here the biggest difference is in the confidence interval that makes the scores more reliable for the simultaneous experiment. And also you can observe that here it is not possible to quantify the difference between these two levels in this case, while here the confidence interval don't overlap, so it's better possible to better quantify the difference between these two points. So why this happens, and one of the factors is because of iconic memory. So this happens when the visual information present in a stimulus continues to be accessible for some time after the stimulus offset. For example, I have here a bottle of water. So if I look at it and then I close my eyes, I can still see it. But even if this information will go away very fast, in fact, it has been proven that the iconic memory lasts between 1/4 of a second and 1 second. So for sure, we cannot take advantage of this type of memory when we have the sequential, because in the middle between the two images, we have this 3 seconds gap with the mid-gray image. But we can we can use it when we have the images placed side by side. Of course, depends on how far the two images are. But this type of memory is also not influenced by the eye movement. So if I focus on an area and then I move my eyes very quickly, the image the icon that was created in the memory will not be deleted. So to go to a further level of accuracy, we have the oscillation or flicker test. And this consists in showing 2 videos to the subjects instead of images. The first video is just done by putting every frame of the video as the original image itself, so it will be just a static video. Here, the original image is interleaved with the compressed one. So if there is any visible difference between the original and the compressed, the image will look like flickering. So this methodology is one of the one proposed in the part 2 of the Aic standards. So in the end, it will look something like this. I don't know if you're able to see anything, also because of the compression of Zoom. I will make this presentation available in case you're interested to see this. But on the left, you have the original. The image on the one presents a flicker, and the subject will be asked to select which of the 2 images contain a flicker. In this case, you will see, if you will see the original presentation, you will see that the image is actually very compressed, because I wanted you to be able to see something even with the compression of Zoom. Usually you do this when you have less compression artifacts, but yeah, still. Okay, so we saw a different way of presenting the stimuli to the subjects. So the first one was sequential. That is good when you have a smaller monitor, because you don't have to divide it in 2 between the 2 images. But at the same time, we saw that it doesn't take advantage of the iconic memory. So sometimes the confidence interval are bigger. So the simultaneous instead take advantage of the iconic memory, but is not sensitive enough to evaluate the visual fidelity, as we saw in Nion's presentation. And finally, we have the flicker that is very sensitive, also in case of minimal distortions, but is too sensitive in some applications. Okay, so we are approaching the end of this presentation. Of course, this is far from being a complete review of the state of the art because of time constraint. For example, we didn't consider the environment that actually plays a huge impact on the results. So there are 2 main type of environments: the control environment. So you can see here an example of the control environment room that we have here at the PFL, where you can select from the ambient light, you can select a big number of factors, or you can do the experiment crowdsourcing. So I will not enter into the details, also because I think that later we will have a presentation on this. But if you're interested to have more information, we have an output document with the review of state of the art, which is available on the JPEG website under the AIC documentation. So just the conclusions, we saw different scales, and we saw that the choice depends on the application. We saw, for example, the example of JPEG AI. We saw different comparison methods. So from the least to the most sensitive, we saw sequential, simultaneous, and the flicker. And in the previous presentation, we saw that the high quality to near visually lossless quality range is still uncovered. So we are looking for contributions for the JPEG AIC Part 3 standard. So these are the references, and thank you. If you have any question, we will keep it for the end.
Thank you, Michaela. In order to not to waste time, I will go directly to the next speaker, the next speaker is Professor Dietmar Salpe. He is leading the work group on multimedia signal processing at the Department of Computer and Information Science of University of Constance, Germany. From 1985 to 1983, he was an assistant professor with the Department of Mathematics, first at the University of California, Santa Cruz, and then at the University of Bremen, which resulted in his habilitation. From 1993 till 1998, he was a professor. He was a professor of computer science with the University of Freiburg in Germany and the University of Leipzig, Germany, until 2002. And since then, he's with the University of Constance. Professor Dietmar is the co-author of the book Chaos and Fractals that won the Association of American Publishers Award for Best Mathematics Book of the Year in 1992. And the book The Science of Fractal Images in 1988, and he's also an author of over 100 research articles. His major research interests are in image processing, where fractal image compression in the past, and now visual quality assessment. And other interests include computer graphics, scientific visualization, dynamical systems, and sport informatics. Please, Professor Salpe, you can start sharing if you...
Yes, thank you very much for the kind introduction, and thank you to the organizers for allowing us to present the work that we carried out in our work group on boosted quality assessment. And I think you will see in a couple of minutes that it's quite relevant to the efforts of JPEG AIC Part 3 for the subjective testing. So let me share the screen here. Let's see, so it's this one, and I go to full screen here. Okay. All right, so this is about...
Sorry, it doesn't look like it worked with the full screen.
Is it not working with the full screen?
Well, we don't see the full screen. I don't know. Maybe you can just keep it as it is. It's okay. We can see the slides.
You can see the picture, but it's not full screen.
It's not.
Yeah, so same for me. I can see okay. Well, okay. Yeah, I guess this is as good as it gets. Okay, so the title is Subjective Image Quality Assessment with Boosted Triplet Comparisons. And this is joint work in our work group of Hui Men, Hanne Lin, Mohsen Janadele, and myself at the University of Constance. And this work has already led to a paper published at IEEE Access, shown at the bottom here, and it appeared in October 2021. And it's a very long paper. It contains many more details than what I can explain here, of course. Oops. Okay, so this is about full reference IQA dataset, not about no reference IQA datasets. And there have been a number of datasets published. Here's a little table of 5 or 6 of them. And I put this table here to point out that the number of distortion levels.
We cannot see the slide. We only see the first slide.
The slide. Oh. So then let me stop the sharing and restart it, I guess. Sorry. Unplug what? I don't understand what you mean. Okay, then. Okay, so let's try again. Okay, can you see now?
Yes, now we see the slides.
Yeah, I'm sorry. It was a technical problem. I was showing it on an LCD screen at the same time, and that caused the mix-up. Okay, so now we are on this slide. So you see a little table of 6 data sets addressed to a full reference IQA. And the table is here to show you that in the past, these data sets contain only very few distortion levels, like 3 to 6. And this does not cover the range of distortions at a fine-grained distance. And we would like to have this, of course, in order to have more differentiation near the high or medium quality imagery. So 5 to 6 distortion levels are not enough, we think. And content providers would be more interested in the high region of the quality 1 JND, 2 or 3 JNDs. And so one of the products of this paper was to have data sets of 12 distortion levels that range up to 3 JNDs measured from the reference image. And also, as was already pointed out in the previous presentations, the DCR technology, where we have 5 integer levels for subjective assessment, saturates very early, and for these 12 levels of distortion, we cannot expect that DCR will work very well. So our proposal is to use boosted comparisons. Boosting is like flicker. Flicker is also a type of boosting, which is one of our suggested components. And we use comparison of 3 images, so triplet comparisons. So what does it mean for a comparison? We have a reference image, and we have a distorted image, and you can look at them side by side and see for distortions in the distorted image. So, okay, and then when you apply boosting to it, like artifact amplification, you get an image that has been is distorted, plus then we added some increments of the differences pixel-wise. So there's a little formula up here at the top. The reference intensity is amplified by, the difference between the reference and the distortion is amplified by a factor alpha greater or equal to 1 per pixel. Okay, so if we have an intensity of 200 for the reference and 210 for the distorted, so we multiply the difference of 10 by a factor of alpha, say alpha is 2. So then the amplification would say we display an intensity of 220 instead of 210. So this amplifies the differences. The second amplification is spatial. So you can zoom into the image to see the pixels more clearly. So a factor of 2, for example, which increases the area by a factor of 4, and so we crop the image and then we enlarge it to make it the same size as before. And there you can also more clearly see the artifacts. And the third one is the flicker technology that was already introduced. So we can add flicker to it. Here you cannot see the flicker because on the PDF it's not shown. So I simulated it would look like this more or less, right? Okay. So those are the 3 types of boosting that we propose. And we will embed this into a triplet comparison scheme. So we have 3 images that we compare. The middle one is called the pivot, and the left and the right are 2 test images. The test images are distorted, and the middle image it could be the reference image, the undistorted one, or a distorted one as well. And then when we do many such comparisons where we ask which image is more similar to the pivot one, the left one or the right one, or maybe we're not sure, we collect all these responses, and from these responses we would like to reconstruct the quality level of all the distorted images for each reference image. And one way of doing it is to use the Thurstonian scale reconstructions from triplet comparisons. And this is something that has not been done in the context of IQA. Here are the formulas. I will not explain it, but you are probably familiar with the Thurstonian idea. The idea is that on the perceptual scale, each stimulus is like a random variable in quality, which is can be modeled by a Gaussian with a certain mean value and with equal variances. And then you can use the maximum likelihood method or the method of least squares, which was used earlier, to figure out the reconstruction qualities of this vector of mu that gives us a reconstruction quality for each of the distorted images. I don't want to discuss the formulas in detail here, but if you have questions later, we can come back to it. So this was sort of the idea, and then we tried to experimentally confirm that this would work well, and we were interested in how well it will work. So how much increase do we get in the sensitivity here? And there are 3 experiments. The first one is the basic triplet comparison, where we restrict the center image, the pivot image, to always be the reference image, the undistorted reference image, and the others are distorted to the left and to the right. And the second experiment relieves this risk constraint, and we allow also an arbitrary distorted image as a pivot in the middle. So we are looking at distances to distorted images, not only to the reference image as in the first experiment. And then we also asked the question whether the boosting would work together with the classic category rating, the degradation category rating, DCR. We did these experiments in crowdsourcing on Amazon Mechanical Turk. It was a very large study overall with pilot studies and so on. We collected, I think, about 1.2 million responses to triplet questions. Okay, so here are the materials. So we took 10 source images from the MCL JCI dataset. These are the 10 images. And then for the zooming part of it, the zoom boosting type, we had to identify cropped versions that we can amplify then spatially to match the size of the original. And the green rectangles here were manually chosen in this case. So here we have these 10 images. They were chosen to kind of have a large variation of content here. Then in terms of distortions, we selected 7 distortion types: color diffusion, high sharpen, jitter, JPEG 2000, lens blur, motion blur, and multiplicative noise. So each of these parameters, each of these distortions has a parameter that governs the strength of the distortion, so we can scale the distortion from low to high, spanning a range of several JNDs. Okay, so in the first experiment, which we call baseline triplet comparison, so this is where always the reference image is in the pivot. We compare two distorted images to the pivot image in the middle. We have 8 types of triplet comparisons. I will explain it in the next slides. So we have 10 sources, 7 distortion types, 13 distortion levels. So this is a reference image and 12 distorted images. And we, in a pilot study, we made sure that these 12 distorted images cover a range of 3 JNDs. And the spacing between consecutive images in these sequences was aligned to be equal or as close as we could get it to a quarter of a JND. That's a very small delta of quality, very hard to see visually with the traditional testing technology. And so, since we were aiming at boosting these differences and making them visible and measurable by these experiments, we aim for a small JND difference between consecutive images here. Okay, so we have 8 types of baseline triplet comparisons, and what's the first one? Well, why 8? We have 3 types of distortions. Distortion boosting. We have the amplification, we have the zooming, and we have the flicker test. So that's 3, and we can turn each one of them on or off. So this gives 2 to the 3 equals 8 different possibilities. Those are the 8 types. The first one is where all the boosting types are turned off. So this is plain triplet comparison. None of these images are processed by our boosting technologies. These are the original image in the middle, and then 2 distorted images according to whatever it is here, maybe JPEG 2000, to the left and to the right, with 2 different distortion levels here. Okay, and then the question is, which one is more similar to the middle one? And then we applied, or the next type was where we look at the A boosting, so the amplification, so the pixel differences with respect to the reference were amplified per pixel with a factor of 2. And then again, we asked which image to the left and the right is closer to the pivot in the middle of the reference image. Type 3 is the Z boosting, and so we only applied the zooming. The next one is, oops, there was a amplification and zooming. There's a typo there. It should be the 4th, I think. And then the next one is a flicker test. Okay, so with the flicker test, we have now 3 images that we have to combine: the reference for the baseline triplet comparison and 2 distorted ones. So we flicker between the reference and a distorted one. So the left side would flicker between one distorted image and the reference, and the right side would flicker between the reference and another distorted image. And then we don't ask, do you see flicker? We are asking, on which side do we have the stronger flicker effect? So this allows us to differentiate between the different levels of distortion. And in contrast for AIC part 2, I think there the question was, do you see flicker? Yes or no? It was a binary decision. But here we have a comparison. We are asking which flicker is stronger, which is a different type of question. Okay, we can combine the amplification and flicker, and we can combine the zooming and flicker, and we combine all 3 of them. So all of them are turned on. So AZF. Boosting, amplification, plus zooming, plus flicker. And that should be probably the most sensitive method. Okay, so those are the 8 different baseline triplet comparisons. And here are the results that we got out of our study for those 10 sources and 7 distortion types, all averaged over those 70 cases for the 8 types of boosting. The bottom dashed line is for plain triplet comparison, so where no boosting technology was applied. And we have those 12 distortion levels here. Oops, 12 distortion levels here. Each level increases the distortion by 1/4 of a JND. And you can see that we did the alignment quite well because the dashed line here is quite straight and it ends at almost equal to 3 JNDs. So this is sort of the baseline that we can compare with. And then the other cases for these different types of combinations of boosting are above 7 curves. And strongest one is, of course, the red line, the solid line. This is the Azf boosting. And this says that as we go from 0 to up to 3 JNDs at the distortion level 12, we are experiencing a perceived increase of 8 to 9 JNDs instead of just 3. So this amplifies the distances by more than a factor of 2 overall. But initially, for the small distortions, up to 1 JND, which is here at distortion level 4, we have a much higher increase of the perceived distortion. And to measure this, we can calculate the sensitivity gain, which is the ratio of the slopes of the red line here for Azf, for Az boosting in this case, and the blue line, which is the plane, the plane case. So initially for small distortion levels up to a distortion of like 1 JND, we have sensitivity gains of factors of 3 down to 2 and so on. And when you look at all the 8 different types, then the sensitivity gain for these 7 types is shown here. So what we see here is a strong sensitivity gains for small distortions, and then there's a saturation effect, but still we have for most cases an amplification going on. Okay, to address this limitation, we did the second experiment, the general triplet comparison, where we now allow a distorted image as a pivot to make sure that the experiment is not going overboard too much. With many cases, we only compared the Azf boosting here, the strongest one, with a plain triplet comparison without any boosting. And here we used all the 10 sources, but only one distortion type, motion blur. So we have 10 images distorted with motion blur, and now we are even more demanding. We are asking for 30 distortion levels spaced over 3 JNDs. So now the spacing between consecutive test images is only 1/10 of a JND. Okay, so then we do the same experiment as before, and we have 2 types of general triplet comparisons, the plain ones and the Azf boosting ones. So for the plain ones, we're asking which is closer to the middle one, and then for Azf boosting, we again ask which flickering side has a stronger flicker effect. And then we do the reconstruction and calculate the sensitivity gains as before, and this is what we are obtaining. Here's the curve for a plain triplet comparison, and now we are getting a curve that is almost straight, and it ends up here at about 4 JNDs, and the boosted version goes up to 30 JNDs. So it increased the gain from 8 JNDs difference to a 30 JND difference, or 30 minus 4. And the sensitivity gain, this factor, then starts here at over 30 and is always above 5 over the whole range. So now with this generalized triplet comparison, or the general triplet comparison, always guarantees a sensitivity gain that is very significant. In comparison, the green curve here shows us the sensitivity gain for the plain, for the plain triplet comparison, where only the reference image is allowed as a pivot. And clearly, the one here with general triplet comparison is much stronger. Okay, we analyzed the results in many more ways, and maybe a couple of slides here. The true positive rate would correspond to the fraction of correct answers. There's always a ground truth, right? We know from the set of the experiment which was the correct answer. We can then count how many answers were correct, and we are expecting that with the boosting technology, the observers will have an easier time to identify the correct answer. And this is this graph confirms this. So the red curve for the second experiment shows us that the true positive rate is much larger than for the plain triplet comparison, which is initially just above 0.5, which is the guess rate, right? Then we also looked at convergence and precision. So what does precision mean? Precision we measured in terms of the confidence interval that we calculated by bootstrapping, the 95% confidence interval. And so we asked the question, if we go for the plain triplet comparisons, for example, in the left graph, and we take 10,000, we collect 10,000 responses, we get a certain confidence interval, which is here the dashed line. And then we do the same experiment with the boosted triplets, and we ask how many triplet comparisons do we need to achieve the same precision, so the same confidence interval, and we see we only need 400 instead of 10,000 triplet comparisons. So the efficiency is much higher with boosted triplet comparisons than with plain triplet comparisons. This was at level 5. This and the other two graphs are for the other levels where we have a higher distortion. And but in each time, the boosted triplet comparisons required only 400 comparisons instead of 10,000. Also, one can look at the SROCC. So we have these 31 images in each sequence, and we know the correct ordering of it, of course, and we can then compare with the ordering that comes out of the subjective ratings, and then look at the SROCC, or the average SROCC of all these 10 sequences. And we see the blue curve for the SROCC starts at 0.7, and the other one is already at 0.94 when we have 50 or 100 or 200 triplet comparisons that we randomly choose from all the triplet comparisons. And so a very rapid convergence to an SROCC of 1.0 happens with the boosted triplets, but not for the plain triplets. Okay, so finally, I come to the third and last experiment, DCR. So there we can only use 4 types of triplet comparisons, so the plain, A, Z, and AZ, but not the flick. It's not possible. So we have 10 sources, 7 distortion types, and here we use again only the 13 distortion levels, and the spacing between consecutive images is again 0.25 JND. Okay, so oops, here's the result. Oh, sorry. Oh, something. Okay, so here we have the result. So for the DCR, the sensitivity gain, again, the factor that changes the slope of the blue reconstruction curve to the red one after the boosting. So we have initially, again, 2 or 3 as a sensitivity gain, but then already before 1 JND difference, so only for the very high quality images, we have a sensitivity gain that is better than 1. Okay, so it works initially, but then it becomes also saturated. So we have this effect here, so that the boosting does not work so well with the DCR, only initially for very small distortion levels. Okay, so we put all our data together, and now we have these 2 data sets. They don't have many contents, only 10 and 7 distortion types. We have 12 levels in the first part and 30 levels in the other part. And the spacing between the levels that's shown in the right image is much more fine-grained than the spacing of the levels in the previous existing data sets. So what are the conclusions? Well, we introduced 3 boosting strategies: artifact amplification, zooming, and the flicker. These enlarge the sensitivity of pair and triplet comparisons and increase the accuracy of subjective full reference IQA. So with fewer comparisons, we can get same quality results or better quality results. So for the reconstruction, we proposed the Thurston's probabilistic model, and we worked out the formulas and the method for maximum likelihood estimation. I showed you only the formulas without explaining much. And we generated two IQA data sets of 1,140 images altogether. We collected 1.7 million crowdsourcing responses in this study. And we have an extensive performance analysis, and I've shown you only 2 or 3 of these criteria, but in the full paper, you can see all these other things in there as well, like effect sizes, convergence in accuracy and time complexity, and so on. So thank you very much for your attention. And so then I stop the screen sharing, and I think I give the control back to the chair.
Thank you. This was very interesting presentation. I'm sure there will be many questions, but we keep them until the end. So the next speaker is Dr. Richard John, who is a senior research scientist at Adobe Research. His interests are in computer vision, deep learning, machine learning, and graphics. He obtained his PhD in electrical engineering and computer science at UC Berkeley under supervision of Professor Frost in 2018, and he also graduated summa cum laude with a bachelor and master degrees from Cornell University. And also Dr. John is a recipient of the 2017 Adobe Research Fellowship. At Adobe, in addition to collaborating with the students, interns, he helped bring synthesis technologies to products such as Photoshop neural filters and Photoshop elements. Please, oh, you're already sharing, okay.
Well, thanks so much for the introduction. I'm just confirming you can see me, hear me, everything's good?
Yes, all is good.
Perfect, okay, thanks so much for the invitation. So this is the unreasonable effectiveness of deep features as a perceptual metric. So this is some work that we did back in 2017, 2018. So I'll go over some of the motivations that we had back then and provide some retrospectives of an impact of the work and how to move forward. So I'm, as mentioned in the introduction, I'm coming from kind of computer vision, deep learning background. And there, we're really looking at, excuse me if I don't sound so good, I was at CVPR, so I definitely got something. But we're looking at deep networks, and deep networks are extremely effective at mapping noisy high-dimensional signals to low-dimensional outputs. For example, can tell us or can classify that this image here is a type of fish, a rock beauty. But perhaps more interesting is that the internals of the network ends up picking up a whole bunch of interesting statistics about the image in an emergent fashion. So it learns by itself what like textures, edges, parts, all that stuff is without us directly telling it. And in this study, we were trying to see if it could actually tell us anything about perceptual similarity as well. So what that means is, given these two images, how different are these patches? If I ask you for a single number, that doesn't really make sense. But to ground it better, I can take an image, just like the previous talk, distort it in two different ways and ask people which one looks more similar to the one in the middle, the left or the right. And now we did the study and humans chose the one on the right, but traditional metrics like L2, PSNR, and SSIM chose the one on the left. And so in this study, we were thinking, you know, do deep network activations actually end up agreeing with humans more often than these traditional metrics? Okay, and why do we believe that this might actually work? Well, around this time, around 2016, 2017, there are these things called perceptual losses that were working really well. and they could do things like take an image, you can stylize it, or you can go from a segmentation map and try to produce a photorealistic image. And these systems were being trained by matching statistics in deep network activations. And they're producing interesting results that seem to certainly look perceptually interesting. Now, there was one problem back then, which was these things were just wholesale being called perceptual losses in the literature, but no one had actually went and verified that they were indeed perceptual in any way. And that's what we wanted to do. And another issue was that what people were calling perceptual losses really came down to one specific design decision. And that was a specific type of network architecture that in the literature is called the VGG architecture. And it was pre-trained on the ImageNet classification task. So we wanted to see, did it absolutely have to be this specific set of design decisions to be perceptual? Okay, so how do you actually retrofit a deep network as a perceptual metric? Mechanically, here's what you do. You have two images, let's say X, X naught. You put them through a deep network, F, and you get two feature stacks there. And then you can compare these two feature stacks by normalizing each of the activations, subtracting them, and then you just average in the spatial dimension and in the channel dimension, and you end up going from two images to a single number out. Okay, so we wanted to ask, how well do the so-called perceptual losses actually describe or model any element of human perception? And if it does well, does it actually have to be the VGG architecture trained on ImageNet classification? So to do that, we gathered a data set. So we had original images. I coded up a whole bunch of different perturbations, such as photometric changes, spatial warps, blurs, compressions, etc. And we could also take different combinations of these, and our distortion levels were continuous. So it's not like I had 5 discrete levels. I really just had an interval that I sampled from there. So it could produce a whole bunch of different combinations and different effects such as these. Now, we not only care about distortions that I hand code up, we also care about things that real algorithms might actually produce. So we actually took deep network pipelines and used those to produce different distortions as well. So I can do that by taking an image and training a deep learning pipeline that's essentially in the literature called a denoising autoencoder. So I take the image, I add some corruption, and then I ask a deep network to undo that corruption. And then I can change a whole bunch of different parameters in that workflow. For example, the architecture of the generator, as well as different learning parameters. In a GAN setup, you would have a discriminator, you could have different loss functions, etc. And from there, you can have a family of generators producing a whole bunch of different distorted patches like the ones here. And for example, if you look at this one on the upper left, I don't know how to write code to actually produce that. So we're able to produce different distortions that you wouldn't be able to describe by hand or in code very easily. These are kind of learned distortions. Okay, and from there to gather triplet, it's pretty straightforward. You take the original patch, use that as the reference patch, and you take two distorted patches on the left and right. And we gathered a whole bunch of judgments on Amazon Mechanical Turk, in this case, about 500,000. One reason we gathered on Amazon Mechanical Turk rather than in a lab was we were inspired by this previous work that showed that many psychophysical experiments could actually be reproduced on Mechanical Turk, even though they weren't strictly controlled in a lab environment. And this enabled us to just go very easily just go large scale in our data collection. Okay, so let's see how different metrics actually agree with these human judgments. So on the y-axis, I show percentage agreement with human judges. Down here, we have L2 or PSNR. It's at about 69% in our data set. Now, this test isn't completely objective. Humans can disagree with each other. So you can check human-human agreement in our data set. That's at around 83. So we're looking to really bridge this gap between L2 and human performance. And so the first thing we do is we show traditional metrics like SSIM and FSIM. They're a little bit better than L2, but they're not making up a large part of the gap. And part of the reason is that these metrics do well when there's a more limited set of distortions, mostly that pertain to photometric changes. But when there are large spatial distortions, which for almost every problem that I care about, that's going to be the case. These metrics are really not designed for that, so they're going to struggle. Okay, so from there we looked at what's called a perceptual loss. That's VGG, trained on the ImageNet classification architecture. And there, we actually see a big performance boost. It makes it about half the ground. And so this is a nice confirmation that what was being called a perceptual loss indeed does correlate well with these perceptual judgments. Okay, from there, we wanted to ask, does it actually have to be the VGG architecture? And so we looked at different architectures, and these are actually older, smaller architectures. And we found that actually off the shelf, they produce better numbers. And if you're coming from deep learning, this is actually very, very weird because right now it's all about scale in deep learning. Everything that's bigger, deeper is going to be better. But it turns out in this case, it's not the case. You have bigger networks and they actually end up transferring worse to this perceptual similarity test by a little bit. Okay, we'll get back to that later in the talk. From here, we wanted to see, does it actually have to be pre-trained on the ImageNet classification task? So these blue bars were trained on a labeling task where you have images of cats, they're labeled cats, images of dogs, they're labeled dogs, etc. We have these other types of networks called self-supervised methods, which are only trained on images without labels. And there's a whole bunch of different flavors of that. There's a lot, they're doing really well now. Back then, these were the kind of state-of-the-art networks. And what we see is that they do pretty well too. And even if you take a deep network and train it with, the first machine learning algorithm that you learn, which is k-means, you actually get pretty decent performance as well. So some of these bars here are higher, some of them are lower. But what we found is that surprisingly, networks actually on this task transfer well, even across different supervisory signals and architectures. And this was really something that was kind of unknown in the literature at that point. Now, it's not just deep network architectures. You have to train on data. So if you take a deep network and just randomly initialize it, it's not going to do so well. So you do need to fit at least a little bit of data, is what we found. Okay, so from here, we want to see if we can actually improve performance by training on these perceptual judgments directly. And how well does this actually work on outputs from real algorithms? And what I mean by real algorithms is, for example, if you have an image here, you could downsample it and run super resolution methods. And we did this for a bunch of really competitive methods back then in 2017. And you get different results that look like this. And you can do this for a whole bunch of different tasks, such as colorization, video frame interpolation, and video deep learning. So we want to see if these metrics are transferring well to evaluating real tasks, that you see in the CVPR proceedings. So what we did was we trained on the previous set of distortions, so the ones I hand coded up, and then we want to see if those boosts by training on this distribution would actually transfer well to real algorithm outputs, if that actually generalized properly. Okay, and so there's a few variants of this. So before we were using what I'll call off-the-shelf networks, where the representation here was completely frozen, and you did simple averaging to get the final result. But you can add a little bit of learning on top of this. For example, you can learn a linear calibration layer on top, and this basically just says, it gives you a linear reweighting of each of the feature channels within the deep network. In this case, the representation here is still frozen, but you can relax that as well, and you can actually tune all the way through to the original representation. Okay, and so this gives you more degrees of freedom. Okay, so this is what we're doing. We have a training distribution on the left. We have a held out distribution on the right. We want to see if boosts in the training distribution transfer to boosts in the held out distribution. Okay, so when we look at off-the-shelf networks, as we saw, L2 is actually down here. So these blue bars are actually already doing pretty well. If you train a linear layer on top, you get a small performance boost. So you get a nice performance boost in the training distribution, and it transfers ever so slightly to the held out distribution. But the problem is that if you tune all the way through the network, even though you do better on the training distribution, you actually get a drop in the test distribution. So it turns out it's very easy if you gather perceptual data and train a deep network on it, it's very easy to just overfit that training distribution because it's very hard to query that training distribution. And at test time, when you're running on real algorithms, you may not have simulated all the different type of artifacts that you saw during training time. And that's going to lead to just overfitting on the training distribution. Okay, so what we found is that the most effective thing is you take an off-the-shelf representation, you just do a little bit of linear calibration on top, and that gives you a little bit of performance boost, but doesn't overfit on your training IQA data. Okay, and so this is what's now called in the literature as a LPIPS metric. It's called Learn Perceptual Image Path Similarity, and you can see more information of that online. Okay, and now it's being used fairly often. So let me just describe some things that have happened since we did this study back in 2018. So one thing is I released the code. It's fairly popular now. You can just pip install it if you're using Python, and it's kind of compatible with different deep learning libraries, and it's being used quite often for a whole bunch of different computer vision pipelines and evaluations now. Okay, I've also been part of some follow-up work following a similar methodology with some differences in the audio domain, learning a perceptual audio metric as well. So this kind of pipeline was found kind of promising in multiple domains, but based on the previous data, it's still not perfect, right? We're still not reaching human level performance. Now, why is that the case, and how do we actually move forward? Well, let me point you to a little bit of further study that was done on our data set. So this was a recent work that's I think really interesting, and their title is on the surprising trade-off between ImageNet accuracy and perceptual similarity. So recall that what we found well is that if you take a network that was pre-trained on a different task, for example, ImageNet, which is a classification task, it does surprisingly well at transferring over to this perceptual similarity task. And this paper was studying how different networks, so different networks will have different ImageNet accuracies. Does that actually translate to perceptual similarity? Is it the better accuracy you have, the better perceptual similarity you have? And it turns out not to be the case. So here on all these different graphs, the y-axis is a perceptual score. And this was run on the data set that we collected. And the y-axis is the accuracy on ImageNet classification. And all these different plots, they're getting different families of dots by varying different hyperparameters in the networks. But even across all these different plots, you see a very consistent trend, which is that first it goes up, positive correlation, then it goes down, which means first the better ImageNet accuracy, the better perceptual score, but then after a certain point, the better ImageNet accuracy, the lower perceptual score. And in fact, this isn't just true for our perceptual data. So this is a screenshot from a keynote from Jim DiCarlo, who's a neuroscience professor. Here, the x-axis again is ImageNet classification performance, but the y-axis is a completely different type of perceptual task. It's how well, basically, it's neural responses, IT responses of monkeys in response to different stimuli. So it's a completely different type of perceptual data. But look at this, they see the exact same trend where you first get positive correlation and then you get this negative correlation. And so this was really interesting to me. It really indicated that there's kind of this trade-off at the end between computer vision performance and perceptual performance. And the unfortunate reality of that is that it means we can't simply rely on just getting bigger and bigger models and getting perceptual similarity solved for us for free, which is kind of unfortunate. In deep learning, we often just go with scale, and that actually works shockingly well. But when we're transferring over to perceptual similarity, it looks like that's not going to take us all the way there necessarily. Okay, so in conclusion, we found deep features transfer extremely well to perceptual similarity, even across architectures and tasks, but different attempts to improve it end up hitting a wall. And for example, I tried training on perceptual data directly, that ends up overfitting. So really producing a better perceptual metric, at least to me, I'm working on some stuff, but it's still an open question. Okay, so these are my wonderful co-authors on this work. Thank you very much.
Thank you very much for your presentation. And the next speaker is Matthias Wien with the talk about MPEG visual quality assessment, remote experts viewing. Dr. Matthias Wien is the leader of the Visual Media Communication Group and the head of administration of the Institute of Imaging and Computer Vision at Aachen University in Germany. He received his diploma and Doctor of Engineering degrees also from Aachen University in 1997 and 2004, respectively. And his research interests include image and video processing, immersive space frequency, adaptive and scalable video compression, robust video transmission, and visual quality assessment. Since 2020, Dr. Matthias Wien serves as a convener of ISO Aic JTC1 SG29 AG5, which is MPEG visual quality assessment. He has been also a contributor to the standards such as AVC, HVC, and VVC. He currently serves as a co-chair of JVET Ad Hoc Group 4, Test Material and Visual Assessment, as a coordinator at JVET Verification Tests of VVC. Okay, please.
Okay, thank you. I hope you can hear me.
Yes, I can hear you.
Okay, thanks. So welcome to this presentation, final one in this session. I'm talking about remote expert viewing that we have been using in AMPEC for a while, which we actually also made some guidelines for. The basic trigger for doing that, so we did some visual testing at AMPEC meetings frequently already since a couple of years. But then we needed to turn that into something that would also work online in order to be able to, well, to perform some visual assessments despite the online situation, which we all enjoy since some 2 years. Okay, so this is something that we have typically been using whenever the trust in some objective metrics was limited. As you probably know, the VD community is in standardization, at least, is currently very much focused still on using the PSNR for evaluations, which is not proving totally wrong, because if you look then at the verification tests of the standards, it seems that the outcome of the process is quite nice. But obviously, I mean, if you study correlations and things like that, then you see that PSNR may not be the true optimum of things, right? Anyhow, so in cases where we, for example, have loop filters or deblocking filters in general, or things like that, there's quite some concern that the PSNR might not reflect the right decisions. So that's why we have some viewing tests included. And this actually is something that, this is actually something that became more important since learning-based tools are also coming into the video domain, and then it starts to be interesting to see how meaningful objective numbers may be if you have this generated content. So how that would typically do, since it's about decision taking. So we would have maybe we have an anchor, we have a proposal, and then the question is which one of the two looks better. So we do A/B comparisons, for example, the test model against a variant of some changes, and then we would try to see how much this differs, and if the difference would be good or bad for the proposal, right? And so this has been employed quite a bit in JVET, but also in MIV, in point cloud coding, and also in the preparations of the dynamic mesh CFP. And the benefit is that we can do that quite quickly, also through during meetings, and it seems to be quite okay, the method. So let me briefly describe how it works. So we need we need a proposal to look at. We have a test coordinator who would basically coordinate the whole work, and then the content would need to be selected. Typically, since it's something that's done during the meetings, and since remote sessions are also maybe difficult to do in terms of distractions and everything, we try to have as few test points as possible. That's something that the group would agree on. Then the material would be provided as MP4 files to the coordinator. There have been tests in the beginning that were taking 10 seconds pieces. Currently, most of the tests actually were taking only 5 seconds, which was found to be fine by the experts, and it has the benefit that the testing is a little bit quicker. Then, well, there's an additional aspect if you think of MIV or point clouds, that you also have to determine something like a viewport or a post trace or a camera path or however you might call it, through the immersive content. We would have some cross-checker or cross-checkers, typically more than one, who check that the MP4 files are actually the correct ones. And then we have the volunteers, the viewers who would be volunteers from the group. They need to provide, well, visual acuity, normal color vision. This is something that we simply ask from the participants at the state. Please recall that this is a express viewing method, so we assume that people are participating in here know what they're doing, and they should be honest in terms of their capabilities. And of course, they need to have appropriate conditions, including layouts and monitor, and maybe also background noise and things like that. And then we'd have something like 15 scores. That is something that we require. If there are lower numbers, which may happen if there are not enough experts to join, then we'd only take that as an indication. And if there would be less than 8, then we would simply say it's not doable. Actually, if something like that would be seen before setting up the test, then maybe the test would simply not take place. Right? The whole thing is currently realized actually by using the VLC player, just because of the fact that it's available for everybody on all platforms. You see here the command line that's currently typically used. So you specify the size from the YAV file that we use as input. Use libx265 for compression. And so here, this line says 10, but this is basically the quality parameter that we use. And 10 is pretty fine. We sometimes also use 15, which is still totally okay. And if you use 10, then UHD sequences sometimes tend to be too demanding for many computers. So in that case, we would suggest that all the content then would be coded with the factor of 15, which is still perfectly fine. Right? And so then there are some configuration requirements on the setup, so that people would have a good setup and can perform the viewing. So specifically, they should basically see the session at once and then just do the rating within the sessions. Session construction would be like this. So you would have this what you could call a basic test shell. So you would either with or without the original. This is the two versions that we look at, and then we would typically say we have a version A, we have a version B, and you see that 2 times. This is specifically nice if you have the 5-second sequences, because then people can stabilize in their votes, and then you would have a 5-second voting time for the current PTC, and people would record that on paper for the time being, right? So for the test session design, we strive not to be exceeding 15 minutes, but rather do some break in between multiple sessions, so that the content would be covered. There would be some stabilization tests, some checks for the test subjects, so that we know if they pay attention or if something strange happens. So that those tests would be comparisons where we know the results, right? So for example, comparing coded version against the original. So the original would be version A or B, or using different quantization parameters in one comparison. So where we know that if there's a higher QP, then the quality should be lower, and so that would be a clear event. So this is something that's then done. And then for the evaluation, we currently have for this comparison task, we have 2 variants. One would be using the 7th grade scale that's specified in I think BT 910, where I would say we have the option. So we have the 2 sequences. Those are randomized, so you don't know which is A and which is B. And then you could choose between 0 and then plus minus 1, 2, or 3, depending on the grade, how clear you find the distances. And then we have another one which has been mostly used by JVET, which is actually more demanding on the for the experts, which is basically taking only 4 grades, right? And so you don't have the option to choose equivalent, but you rather say that A is better than B or B is better than A, or you would say it's much better than the other one. Those are the 2 options that you have, and so this is a forced choice, and the reason behind again is that the expectation is that experts would be capable of doing that, so they would be forced to draw the decision and then take it. And if something's really, really close, then it would average out somewhat around 0. But this is, I mean, the numbering is something that has been used again for quite a while in JVET. I think that was something that first was used in 2018 or in 19 or so. So in that case, people could not score for equal. This means that they couldn't take an easy life and say it's just too low, so I don't look at it close enough. Maybe we also have used the same setup, like doing this remote thing with the MP4 files with other methods like DCR, ACR, at various meetings for different purposes, and that also worked quite well. So it's something that we found quite helpful. If we go back to physical meetings in October, I think we are expecting to do that. Then we might just do the same thing, but then in the situation in presence with the in a room where we can do the viewings on site, which I think is better than online. But we have to do it the way it is, right? So the collection for the data then is. So we have some demo, actually also some training, which I think I missed to put here on the on the bullets. But so the demo would include material that is meant to stress the computer so that you can see that the playout is fine, that the display is okay, and things. And then you would have the data which you actually are supposed to vote on, which is password protected. The idea is that there would be a joint session, a Zoom session for the coordination of the tests, including the training and informing the participants. There would be, with the test material, you have the instructions how to vote and voting sheets that people should print out so that they have a very low amount of effort to put their vote later on into the screens, into the voting sheets. And the idea is that they should not be distracted too much during the viewing session, and it should be done in a row, right? So as I mentioned before, the participants are not supposed to, to change the speed or even pause the playback to study some stuff closer. It's really just this kind of one-shot impression that they have, and this is what we want to record. And then so we have the online meeting where we do the introduction, then people get the password so that they can unzip the material, and then they can actually start and do the processing then by the participants, right? And so as I just mentioned, so we say that people should score on paper. And this, I think that's really important, because if they struggle with something like a tablet or whatever, they're not focused on the viewing test, but rather do something else. And this should not be, because they would be distracted. And so, of course, within the meeting, we could have multiple sessions, so that along, rather than doing one long set, we would maybe have something like 3 sets of 10 minutes or so with a break in between, maybe also collecting some impression on the structure of the test or so. And then for entering, we have a website where people basically provided the password and login credentials so that they can type in their data, so that we have it in a database and can directly process that for a speedy evaluation. And so you see here a small example. I don't know how well it's visible, but people have actually the option to leave also comments, so that they see if there's something wrong with some aspects, or if they find something specifically difficult or so. And then in the evaluation, so what do? We de-randomize the assignments, right? So and the sessions, of course, we have the computation of the MOS and the confidence intervals. We have we do this. We look at the checking of the test subject. We look at outliers, and we look at the correlation of the scoring of the test viewing persons against the MIS, and then we produce some plots. And this is just some examples with some maybe typical results where we would say, so since we are on the scale between ±3, so you see here, in this case, the experiment might have revealed that the proposal would be better. So positive number would be in favor of the proposal, negative number would be in favor of the anchor. So that one would be clearly better. This one is almost at the edge because the confidence interval is pretty close. This one is worse. And you have also some cases where you might not draw a decision because the interval is too small. The confidence interval is too large and the distance to the zero is too small. And in these cases, you would say there's no effect. Right, so this is basically how it works. And the method is under study currently. Our goals are that we basically want to make it as robust as possible. Yeah, so to use it further for experts viewing, I put the R into brackets because this is obviously something that we could also apply on site when we have physical meetings. We want to use that information actually on top for the study of objective metrics, because this process is still quite exhaustive and time consuming. So if we can somewhat justify that there's some objective metrics do provide sufficiently reliable results, and then the recommendation of AG5 might be that those metrics would be used for evaluation of the tools rather than running tests. So that's basically a side activity. And we do this by we have a report where we basically study test metrics and also look at databases. And this is the document N58. You see down here, you see a link. And actually, I think if you probably will be provided the slides later on, but this is something which is publicly available anyway. So this is something that you can get. And so currently what we just had as a recent result, this is what I don't want to go too much into details, but just mention it. And also because Richard is here and the ILFIPS is also included in the set. So we see some evaluations on the number of metrics. That was actually 17 different metrics, including some with full references, which are the upper ones here, and some with no references down there. And then basically just looking at how well those work out, and seeing that some are actually working quite well. So including those that you see here, actually you see that, so if you just look at there were different constraints in which the analysis was done, but actually the PSNR was not super bad in some cases. But you see that also some others were not so reliable at all. And specifically for the non-reference metrics, this is something that we kind of expected, but for the task that we are doing, the comparison to the reference probably makes a whole lot of sense. Right? And so that's basically it. What we are up to. So we have that method. It's being used, and I think it also has some merit in the evaluation of the group. And it's actually mostly used currently for new coding tools, specifically for those which are using deep learning based methods, because there the uncertainty on what's happening is the highest. We are working on studying the method and trying to refine it, study the correlation with objective metrics, and also what we're doing is to study the performance in relation to other test methods. So like running formal tests on the material that we have been using for these evaluations, and then seeing how well the experts methods that we are doing actually matches what's going on when you do it with a formal test with naive subjects in the laboratory, right? So that's something that's also going on. And, well, we want to stabilize that a little bit further, and then if you feel confident enough, we might well try to do some advertisement of the method, and maybe reach out to other interested organizations or standardization bodies. And that's it for my presentation. I thank you for your attention, and I probably give back the screen to Evgeny.
Thank you. Well, now we are ready for the panel, let me show the speakers. We already have quite a few questions in the chat. Some of them are already answered. Do those people who asked the questions want to actually say them, or we keep the answered questions in the chat and then only ask the unanswered ones?
I think for the recording, it might be good if they are repeated, because I think they're not captured in the recording.
Yeah, okay, just a second. I need to open the chat. There was a question from Jon about
yeah, it was just a small question about how you know the correct order when you're talking about true positive rates, the correct order if the distortion types are different, but apparently in this experiment, the comparisons were within the same distortion type, so the question didn't really apply.
Yeah, okay, I see. And the next question was from Turaj to all speakers, and actually there were two questions. One is how to take into account content and context in subjective and objective quality for the future AIC standard. We know that in addition to content, there is also context, such as display type, environmental illumination, distance between subject and display, etc. And how would they impact quality? And the second question is, many subjective protocols come with various recommended statistical tools, such as outlier detection, significance test, etc. Should AIC3 propose some of these as well, in addition to the quality assessment protocols? This question was already answered by Dietmar.
Should I explain it?
Yeah, sorry.
Should I explain it, or do you want?
Yeah, sure.
Okay. So regarding the first question, since this is a crowdsourcing environment, I think the devices are very diverse, and the context is very diverse, and one should control for it to some degree, not too much. For example, it would be nice to have ensured that the visual angle is the same for the displayed images, so that we know the resolution in terms of how many pixels per degree, per angular degree of the view are there. So because otherwise it would not be so easy to compare the different ratings with each other. So with this, one can use like a credit card test, or to match the size on the display with a credit card that is held in front of the display, and then one can tell the observers to keep a distance of 50 centimeters or something, and then one knows what the angular resolution is of the image. So this is probably useful. And also one should probably not put into the same pot the ratings achieved by observers that use a smartphone and others that use a very high resolution, big wall display or so. So there has to be some restrictions about this. I don't know about color blindness, whether this is should be also ensured that people have normal vision. All these things, or some of these things, have been added in previous standards and probably should be also included here, in particular because it's a crowdsourcing. And the second question was about the assessment protocols with recommended statistical tools. And I think this is a very important issue. If we go for pair comparisons or triplet comparisons, as we have done them in our contribution, we need to make sure that people that use this reconstruct the scale values with a mathematical method that is defined, because other people can use other methods for reconstructing values from pair comparisons, and there's already quite a variety of such approaches in the literature. So if we only prescribe, okay, you do pair comparison and then you reconstruct scale values any way you want, we will have a problem. So I surely recommend that if we go for comparisons, then we must also state how to evaluate these comparisons and how to transform them into a scalar value. And then another important issue within that context is the precision. It would be nice to have, like the variance for the MOS, it would be nice to have a precision also for these reconstructed scale values. And what we have done consistently is to calculate confidence intervals, 95% confidence intervals from bootstrapping. Bootstrapping is quite standard and easy to understand, easy to interpret, and so one would have to resample the same number of responses from your comparisons and reconstruct from these resamples many times, and then one has reconstructions like 1,000 or so and can calculate those 95% confidence intervals. So that will give us then a handle on the quality of the data sets that we will obtain. Outlier removal is another important aspect, in particular, more for crowdsourcing than for lab studies, because there are many crowd workers who are in there to very quickly, get the job done without taking sufficient care, and one would have to identify those and remove those outliers on a worker basis or on a job basis, so like on a hit, or even per question. And for this, I would suggest to have a robust outlier removal. The robustness means that if you apply the outlier removal technique and you get some outliers and you remove them, then if you do this this thing again, that you will get the same outliers and not other outliers, right? So that is the robustness there, and so we have a suggested procedure in this paper and also in other papers. Yes, and was there something else? I think those were the main issues.
Yeah, I guess that was it. I just I have a little question from myself, just as a clarification question to your answer. Like when we talk about the screening of the subjects, like you mentioned, color blindness, do you think it will be compensated like by the number of subjects? Would be vanished any kinds of like vision deviations, or we need to somehow count on it?
Yes, I think there's a trade-off, or both things. The detection or the identification a priori of subjects that should not be in the study, and later on in the outlier detection, those serve sort of the same purpose. And outlier detection and also like bias removal are techniques to identify these subjects or these sets of ratings that should be regarded as outliers or not useful in the study. So one does not have to be extremely strict on either end. I think it is okay to leave some outliers in the data and then remove them in this outlier procedure, right? So one does not have to be strict and sort of make a test and then not consider these outliers at all anymore. So in bias removal, some proposals for bias removal are to the point that you should not remove any outliers, but then the bias removal technique will assign very low weights to these outliers so that they don't have much of an influence on the overall reconstruction scales. So this is an alternative to strict outlier removal, and that can also be considered.
Okay, this is very interesting. Okay, thank you. So I will repeat the questions one more time. Maybe anyone else wants to answer them because they were to all the speakers. So first one is how to take into account content and context in subjective and objective quality assessment. As we know, in addition to content, there is also context such as display type and illumination, distance to the display, etc. And the second question was about many subjective assessment protocols come with various recommended statistical tools, such as outlier detection, significance tests, etc. And should the future AIC standard propose some of these additional tools? Anyone else from the speakers wants to answer these questions?
Maybe a question on top, because I think this probably depends on what you want the testing conditions for this new standard to be, right? So do you want this to be a test that's like lab conditions, or do you want it to be a test that's emulating something like user behavior? I guess that should have a strong impact on the setting that you would allow or that you would specify, and specifically if it's towards this kind of consumer type of evaluation, then you might need to have some kind of specification of some, I don't know, testing or calibration methods so that it's somewhat reproducible, right? That's just a question because I'm not fully aware of what your intentions are here.
Well, currently we are considering both lab environment and crowdsource environment as like two different parts, two different kinds of subjective evaluations. And I guess your comment is very valid. We should probably have different suggested procedures for statistical analysis and outliers detection for these different approaches. So this is a valid point. I agree.
So about viewing conditions, I think there is in a crowdsourced environment relatively little control over them, in the sense that you can instruct the participants to do things a certain way, like have a certain viewing distance and so on. You don't really have a guarantee that they will actually do that, and they will not consciously or unconsciously change their behavior during the experiment. So the few things that you can record, though, I think are good to record, and basically that's very limited, especially as browsers are increasing the privacy and the fingerprinting options that they give. But you do know still the screen resolution, the device pixel ratio, and the user agent string. That's basically the only real information you have. So you can distinguish phones from desktop or laptop environments that way. That's, I think, a very important distinction, because the viewing condition on a phone is very different than on a laptop. I don't think we necessarily should restrict things, though, to only desktop and laptop. I think in the past we usually did, and but mobile is also a very important use case, and I don't see why we shouldn't investigate quality as perceived on mobile as well. But it should be recorded, and maybe it's an interesting research topic to see how quality is perceived differently on mobile versus laptop. In general, there's very little control possible besides, I mean, you can give instructions, but there are going to be participants that ignore instructions, whether by accident or on purpose, and it will be really hard to enforce.
Okay, thank you. The next question was from Turaj also to Richard. What is the impact of the trade-off between computer vision task and perception in optimization of codecs, such as JPEG AI, where high perceptual quality as well as high performance vision tasks are desired in applications where the same images are to be used by both humans and machines? I guess maybe it needs a little bit of explanation here. So at JPEG AI, the codec is supposed to encode the images that should be possible to decode by a standard decoder for human perception, as well as by tools such as image recognition tools. They should be able to work with the compressed data in the compressed domain. And I think Richard already answered something, but maybe he wants to comment.
Got it. Okay. I think I didn't quite understand the original question when I answered that. I see. Yeah. So I guess that trade-off I think is a separate thing. So that trade-off is saying if you have a really big, deep network trained on some other task, it likely won't do as well for perceptual similarity. But if you're doing perceptual similarity, you should just use the best perceptual similarity metric that you have, which currently is, for us, is kind of shallower networks. And then I guess what we're saying is, okay, so in this case, you're saying JPEG AI is a type of codec where it not only preserves information for perceptual similarity, but also for downstream tasks to use. And I guess there's probably an inherent trade-off there. I'm not an expert on that as well. So that's something that would be interesting to study. Yeah, I'm not an expert on that.
Okay, thank you. Well, if you're interested, you should check the JPEG website. There's a lot of information about JPEG AI. Okay, so the next question is also to Richard from Thomas. Have you tried to assess the performance of deep learning methods dependent on the GND of the distorted images compared to traditional methods? One might expect that for high quality images at the visual threshold, deep learning methods probably do not offer much of an improvement. However, they may offer quite substantial improvements for larger distortions. Is that the case, or do you have some data to back up such a guess?
Yeah, that's a great question. I'm glad that was brought up. So I didn't bring up in the presentation, but in the paper, we actually did a JND test as well, because we were kind of concerned about this. So our concern was that the triplet test is actually not what they call cognitively impenetrable. Like, you know, it could be just depending on time of day, how you feel, suddenly you feel one type of distortion is closer than another. So we ran a JND test where you have an image, then you flash an image, you flash a distorted version of the image at a certain distortion level, and then you ask the user if it's the same image or not. And sometimes we also flash the same image twice just to kind of keep things balanced. And then we ran a correlation between different perceptual metrics, deep learning based perceptual similarity metrics, and these two perceptual tasks. And if you look at figure 5 in our paper, there's like this really strong correlation between the two. So yeah, it turned out somehow deep networks just provide this really well-calibrated space where even for low-level distortions at the J and D level or at higher levels that our original test was in both cases, they actually described things pretty well and had strong correlation.
Okay, thank you. We don't have any more questions in the chat, so if anyone wants to ask more questions, please raise your hand. And I see no hands. We are already 20 minutes beyond the schedule, so I apologize for that. I think this was a very nice question session. We had some very interesting questions and some discussion. And I would like to thank everyone for coming, the speakers and the participants. I hope that you will be maybe more interested in this in our activity now, and maybe we expect we want people to contribute to the new standard. So if you are thinking about it, please contact the chairs. We will be happy to explain to you more what we are looking for and what it's going to be. So I think I would like to conclude this this workshop, and I wish you a nice evening or whatever time of the day you have there. So thank you very much, and goodbye, and maybe see you at another workshop.
Bye.
Bye-bye.